Our next presenter is Dan Haehn. He's from Children's Hospital Boston. He's a research programmer. And Tiffany cut off the title, the topic. She has WebGL for baby brains, which is what Dan wanted to have originally. And I was afraid if we put that up there, people would think it would be like, WebGL for dummies kind of presentation. But it's actually a very complex, interesting topic, neuroimaging in the browser. So he called me up, well, he sent me an email and sent me some links and said, do you think that this is like worth presenting? And I was like, wow. So I'm really happy he contacted me, and I'm glad he came down from up north to do this today. So Dan, go ahead.
So thanks, Monty, and thanks, JHT, for hosting. So far, we had a fun event. And so my name is Daniel Haehn, and welcome to WebGL for baby brains, neuroimaging in the browser. So our motivation is, you see a lot of movement concerning games or animations with WebGL, but we actually use it to display research results at our facility. So I am from Children's Hospital Boston, which is the largest pediatric hospital in New England, and also the primary teaching hospital of Harvard Medical School. And I have to say, it's a fun place to work at because it's geared towards kids. You have like cartoon figures all around, and we have clowns. We have robots who deliver the food among the patients. And so Children's Hospital Boston has about like 10,000 people working there, and we are part of a group called the Fetal Neonatal Neuroimaging and Developmental Science Center. So that's quite a mouthful, so it's a short FNNDSC. And yeah, we are an interdisciplinary research group. This means our members are physicians, psychologists, physicists, bioengineers. And our director is Ellen Grant, who is a physician and neuroradiologist. So you can visit our lab website at childrenshospital.org/FNNDSC. And we also have our code portal set up at fnndsc.github.com because we are big fans of open source software and open research. So you can check it out. So I am here today with the two other guys. We are the computer guys of our lab. And so here there's Nicolas Ranou and Rudolf Pignat. And here you see figures of our heads as MRI volume rendering. And actually that's WebGL. So we can turn it around. We can zoom in, zoom out. So if I press enter, the opacity gets adjusted, and you can see into our heads, see the actual brain, and that's the MR volume rendering, which I will explain later what it actually is. So when we talk about neuroimaging, all starts with the MR scanner. So the MR scanner, we like to tell the kids it's a brain camera, because you can see inside the brain. So here you see like a 1-year-old getting ready for her MR scan. And here she's laying down, and the thing on top of her head is a so-called coil. The coil enhances the signal-noise ratio very much. So she lays underneath there to get better contrast, better imaging contrast. So MR works like with a strong magnet, which stimulates the molecules of tissue, and due to different relaxation times of the tissue, we can map it to intensity values of like an image, So so when you do MR scans, you sit outside at a scanner console, the patient is inside because the magnet is so strong, it's like 1.5 Tesla, 3 Tesla, or even 7 Tesla, that the room has to be MR safe, and all metal objects have to be removed because otherwise it's very dangerous. You can be killed, if something gets sucked into the scanner when you're laying there. On the other hand, being scanned by MR is completely harmless for the patient. So that's why we can scan even pregnant women and analyze the fetus inside the stomach. So, what I wanted to say, the fetal neonatal of our lab, fetal neonatal neuroimaging and developmental science center means like babies inside, unborns and toddlers, this age range. So here's, you see a different type of coil, which is very small actually. I put the Sprite bottle there to see the comparison, how small the kids are we can scan. No matter what kind of like strong magnet you use or what kind of sequence you use on the MR scanner, you always end up with a volume, an image volume, which is constructed by the slices in scan direction. So you can imagine that if you scan your brain, you have like slices like going like this in a 1 millimeter distance from each other to get the image cube. And those image cubes can be resliced arbitrarily in any direction. So here we have a brain of a 10-month-old child, and we can slice through the cube through the orthogonal directions like that, from left to right. And you can threshold the image to highlight specific features, you know. And if I turn it around, now I can activate volume rendering on this guy too. And here you see like the baby, you know. Looks dead, but it's not dead, you know. So yeah, when you have this volume, researchers work on it by segmenting out stuff. And that's like a tedious process. Imagine all the slices. A volume has usually like 160, 170 slices in the scan direction. And to segment, it means like labeling different structures. And so researchers can work like a month on one data set to have it completely labeled when they do it manually. But there are also automatic segmentation methods, which of course, since we're computer guys, like much more, you know. So once you have a label map like that, you can use the marching cubes algorithm to generate three-dimensional surface models. This one is WebGL again. You can see that's the brain hemisphere of this guy we just saw in the volume rendering. Another option of scanning is called diffusion imaging. And through a special sequence and some pre-processing, you get a FA color map, it's called. And this FA color map lets you see connectivity inside the brain, which means what regions are connected, which regions are connected to which, kind of by analyzing where the diffusion of water goes, you know. And so once you have this FA color map, you can see brain tracks, yeah, the regions, how they are connected in the brain. So this is the corpus callosum, which is the middle part sitting between the two hemispheres of the brain, connecting left and right hemisphere. And it's an important structure. And you can zoom in. Oops. It's like GL line primitives rendered with WebGL here. And yeah, we also call it the Mohawk, you know. So in the past, all this image processing and visualization was done with specialized software, which had to be installed. Like, for example, 3D Slicer, which comes from Brigham and Women's Hospital. It's pretty popular in the medical imaging field, and it's platform independent, but you have to install it. It's a big package. Or like Freeview, which comes from MGH, Mass General Hospital, and Osirix from Switzerland, or TrackVis. So last fall it started where we were thinking, how can we bring this stuff to the web, you know, like without the need of specialized software. And so there are many WebGL frameworks, but if you think of researchers who like color images or like write algorithms, they don't want to do computer graphics programming. They don't want to do any program in the best way, you know. So if they code, then they do MATLAB analysis. So we came up with an approach. We named it the X toolkit, you know. And so maybe you developers have remember like when you used to use the X toolkit intrinsics for the for using for programming X windows, you know. And we thought the tool has like has bad experiences using the X toolkit intrinsics. So we want to give it a new like flavor. With like we made the X toolkit having a simple visualization API geared towards scientific visualization. So in our world we have a bunch of file formats like STL, VTK, which can be which are popular to exchange the medical imaging data. So we made it that they are supported out of the box in WebGL. So the idea was, if researchers want to visualize something on the web, they just put their files, which they have already on the web, and write only little code to have a rich interactive 3D visualization using WebGL. On the other hand, we wanted to focus on the software development process because we came from the application development world, where you have like a lot of builds, testing systems. And of course it should be open source and fully unrestricted. So actually the XTK is now released under the MIT license and available. So let's look at the slices of the 10 months old again, which I showed before. You know, to do stuff like that with the volume rendering, the thresholding and stuff, you can, and the slicing, where you move through the volume, you can do it with little code, with using the X toolkit. You can write, yeah, it's like 7 lines of code actually, you know. So it works like that. You have a diff in your HTML page. So you create a new X renderer with the ID of the diff. Then the renderer.init call creates the camera, the shaders, all hidden, but can be overloaded for more flexibility. Then you say you want an X volume, the volume for the image volume, and load it from the nerd file. So when you acquire a scan with MR, you get it as DICOM format, which is a folder with like each slice as a single file. But a common approach among those researchers is to generate it as one single file volume, which is called a nerd. They call it nerd format, you know. And so when you add it to the renderer and then say renderer.render, it's there. The rendering, the file will be loaded. You see a progress bar, and you can interact with the thing. Let's look at the surface model again. I loaded the hemisphere. So it's the same principle. You create the renderer, this time in another diff ID. This time you create an X object. So only for volumes we have to use a special class, a subclass of X object because of the slicing support. But for the brain fibers, which we will see next, or the surface models, they are all X objects, which you load in. And then you can simply set the color, add it to the renderer and render. And this would be the result. So here's the corpus callosum again, the structure which connects the left and right hemisphere of the brain. And it's the same approach. Create an X object, load the TRK file, which means tracks, fiber tracks, and it renders like that. So when you put those things together, you know, those components I just showed, you can make nice demos like this, which shows the two hemispheres, and with the fiber tracks of the whole white matter surface, it's called. And this graphical user interface is called det.gui. It's from, I think, from some Google guys, and it clips right in. So you can attach the volume and the visible attribute, and then you don't have to do anything. The checkbox gets defined, and you can change the colors the opacity with only little lines of code. So if you don't want to write any code, we made an exporter for 3D Slicer, the software which is used in medical imaging. So if you add your stuff there with just a menu and point and click end user application style, then you click one button and it exports to WebGL using the XTK X toolkit framework. And it copies the camera settings, copies multi-view, and the colors of the stuff. So here's another model, not the brain this time, but the the abdomen. So it works also with a large. That's a large data set. Yeah. So here's another one. You can change the background color, and here you see it's a feature. When you hover over it, it can show, the X toolkit can show a caption. You know, I will just demonstrate this later. But 3D Slicer itself doesn't have this feature even. So let's talk about the internals of the X toolkit. So we are based on the Google Closure library and the Google Closure compiler. We liked it because it has the nice dependency mechanism with goog.provide, goog.require, and has a great event system where you can communicate among different classes without knowing each other, just by firing events. And we used to know this principle from with Observer and stuff from application development. And it has easy object inheritance and nice unit tests. The Google Closure compiler checks your code when you compile, and in an advanced compilation mode, it's very minified. So we liked it, and we checked a bunch of libraries out there, but this one fitted our need. So if you look at our distribution server, get.goxdk.com, you will see a bunch of files there. It's maybe hard to read, but I can read it for you. So the xdk.js is the latest stable release of XDK. Then you have xdk-edge.js. It's the most bleeding edge version of XDK, built on every change of the master branch. So we're using GitHub to do the development. So if somebody merges something to master, it triggers automatically on the server a rebuild of this library, so you can test with this JavaScript. Then we have XDK Nightly, which gets built every night. And here you'll see XDK release 1, 2, and 3. Those are the 3 releases we have so far, and we started in January. So the first release is the 12th of January, the second the 12th of February, and the third the 12th of March 2012. So our release cycle is every 12th of the month we bring out a new release. And the first XDK release 1 was 327K. Compressed, you know, that's long. That's a lot. Then we activated for release 2 the Google Closure compiler advanced compilation, and it turned out it was 107K afterwards. So release 3 added some features like the volume slicing. So now we are at 120K again. And the last file is the dat.gui from Google, I think, or Chrome experiments, which we had to modify a little bit to directly plug it in. But if you link to this file in your HTML, you can use it. So that's very small, and I'm afraid I can't make it bigger, but it's the build system in action. So our build system is based on Python and uses the Google Closure compiler. So we set up all the passes, run it through the compiler in advanced compilation mode. Then you see the code was compiled. And what happens then is, depending on which kind of build you specified, experimental, nightly, or continuous, it gets pushed, uploaded to a C- system. I don't know if you guys know C-, but it's open source software for enhancing the software engineering process. It has a web interface where you see each site which built under which platform, which kind of software, nightly, continuous, or experimental. And you see like build warnings, build errors, build tests. So we wrote the interface from the Google Closure compiler to work with the C-. It's like XML files which you then push to the server, and then C- parses that. So every day you can check immediately the automatic builds we set up if something broke, you know, after you push the change on different platforms. That's the idea. If the tests are failing after a change or after, yeah. So right now, if you go to c-go.xdk.com, the dashboard will be empty because we're working on some testing. But I took the screenshot like 2 days ago, and you can go back in the past and look at the results, how it looks. If a test fails, you'll see where it fails and why it failed and stuff. So what we don't have set up yet, is testing with like frame rate testing. We would like to set this up using like an XV frame buffer to run the tests in the XV frame buffer, parse the results, automatically upload that. So so we're using Selenium to communicate with the tests of Google Closure Library. So if somebody has an idea or like it has done something like that, I would be really happy to know about it, because I think that's very important. If in the JavaScript world where we just do scripting, that we still like enhance the code quality by constant monitoring. So the X Toolkit API is the documentation of our classes, which we wrote. So it's all documented using JS-doc and gets generated on each new release. So it's publicly accessible under api.goxdk.com. So there were some challenges during development. So first, the file input output. So our data can be huge for web purposes. I think it's like sometimes around 100 megabyte. The data can be in different coordinate systems. We can, for example, right anterior superior, which is a right-handed coordinate system, and no, it's a left-handed coordinate system, or left posterior superior, which is the opposite, and we had to like adjust that everything like fits well together when being rendered. Another problem was that some data requires partial or full unzipping. And we did not want, our main goal was that the researchers can just throw the files on the server without modifying them or like passing them to JSON or whatever, just like put it there. So we needed to make unzipping work on the client side in JavaScript. So we used JXG's unzip library, and it works well, but it can be slow. So if you unzip like a 60 meg file, it can take maybe like 30 seconds, 20, 30 seconds. So it's not ideal. We would like to work on that. Another challenge was the transparency and blending, and I think many WebGL developers have problems with that. We need to order by depth, right, from back to front to make it work properly. So what we have is object-based depth ordering. It works well. So every time you move the camera, it checks which objects are now in front and like draws them last and draws solid objects, fully opaque objects first and stuff. So this works well, but some artifacts appear because we don't order on triangles, on primitives. We order on object-based. And I will show you soon what this looks like. Yeah, we are open, like if somebody implemented depth peeling, I don't know if it's possible at all, but I would like to see that, or if somebody has other suggestions for this issue with the transparency, that would be great. Then we ran into some performance issues during development. We have then optimized our loops. You probably know the fast stuffs device. We like this approach, doing unrolling of a loop, and it makes it faster. We did some tests, and that's great. So when we communicate among the classes, among the objects internally, we only access properties without validation. But if we provide an API to the user, it validates the inputs and throws an exception if something is wrong with the inputs. We also use caching in local variables and stuff like that. We read some JavaScript performance guides and hash maps. We use hash maps of the Google Closure Library. Okay, let's go into the demos. And I have one open here, which is Myung's Baby Brains. It's called. This is from a researcher in our group called Myung Soon. She is a physician. So she recently made this demo to accompany a paper she submitted. So here we see 6 baby brains of different ages, from 3 to 13 months. And if you move them around, and release the mouse, they all switch to the same position. So you can see like a size comparison of the different structures of the brain. So here you see like the cerebellum, how it develops over time. The cerebellum is the yellow structure here in the bottom of the brain, and yeah, it's interesting. Then you can switch the views to different views. For example, the medial view of the data. So it's the one hemisphere is gone, and you can see the details, the deep structures. So if I hover over with the mouse, it will show me which structure is which. So it could be interesting for other researchers to see the results. We also have the thalamus, for example, which then makes the hemispheres transparent and just shows the inner structures. And here we have the depth ordering, and I think we'll see some artifacts. Let's see. Yeah, you see this flashing. You see the flashing in the it's hard to see, but yeah, here, see that? So in doing the depth ordering, you know, this gets moved back and forth, you know. So then it's viewable, right? Yeah, I'll show another example for that. But yeah, that's the problem with the depth ordering. Yeah, there are different structures. You can center the brains again. So let's go to, so our main server is goxdk.com. If we go there, we get forwarded to the GitHub page. Oh, here. So we get forwarded to this page and here. So we have a bunch of demos online and also a bunch of lessons, you know. So for example, to get somebody started easily with the X toolkit, they can work through the lessons which are heavily commented. This cube is done in 3 lines of code, for example. But I want to show this guy now. Let's move out of this. Okay. So it's loading right now, and this is about 80 megabytes of data which gets downloaded and parsed right now. And it's a brain atlas of a human brain this time. So it was an adult brain, sorry. So those are 150 different structures labeled, and so 150 different objects. So if we hover over, it shows the title of the objects, and here we can see the medial view again, the thalamus. It's completely parcellated. So here you see like the names of, that's a corpus callosum, which we saw the fiber tracks going through before, you know, which connects the left and right hemisphere. And yeah, and here it's clearly to see the artifacts with the depth ordering of the opaque hemisphere. You know, it just jumps around, and yeah, it's not, could be better. So we are looking for a solution for that. Here you see the limbic system, which is my favorite because it looks like a scorpion. Yeah. Another demo is maybe interesting, this one. It's the brain fibers of a whole head of a 2-year-old. This is data collected at our hospital. And here that's the whole thing, the whole head with the brain fibers. If you zoom in, they're all like lines. And the different colors mean the orientation. So red fibers, or partially red fibers, go from left to right of the head. Green go from back to front, and blue from up to down. So if I hover over, it shows different regions of fibers, different fiber bundles, which all have different functions, of course. You know, that's how the researchers like check if a kid is healthy, if those fibers can be broken through a head injury or something. So if I now move the head to the other side and do the same thing, you know, then I think this one is the real opacity. But like since this one is very dark, So that's a strange artifact, which I think is connected to that this whole head is one object, so we don't order each fibers, you know. I don't know if this would be performant at all if we would do that. But so we don't do depth ordering here and get this artifact. So here it looks like that, but from this side it looks like that. It's like it's connected to the normals and the transparency. So if somebody has insight, it would be great. Another interesting demo might be this one, the Anorisk Web database, which is was created from some friends in Italy, who that's a a research project funded by the European Union. So it's a database of brain aneurysms. Brain aneurysms means like blobs of vessels where like they can so blood gets stored in those blobs and they're not normal. They can burst and you need surgery, brain surgery. So if we go ahead, he made this nice interface where you can search a relational database with clicking the buttons. So case status is ruptured, you know, which is not good for aneurysms. We click search, and then it comes up with all those cases. If we click now preview, it loads a XDK renderer and shows the data set here and to interact with, and then you can go down with the opacity, see the center line of the blood vessel and the neck plane where the aneurysm has to be cut to do surgery. So I can pan too if I hold the shift. Here's the neck plane. So it would be cut off there at the right plane when there would be surgery on this case to avoid the explosion of the aneurysm. This data, you know, can be completely downloaded with surface, DICOM volume. So we are big fans of this open research, open science approach where researchers not only publish papers and then you see like a 2D image and you don't know what's behind, you can't turn it around. We are fans of like having the data accessible on the web. So maybe like publishing a paper, but then also having a web page where you can see and actually look at the data in 3D. And I think that's quite possible with the XDK. And as we've seen here, the researchers do that now, and I really appreciate that. So let's look at this demo, which is a heavy one. It's let's see if it loads over the Wi-Fi. It's actually my brain with some surfaces. So this renders then 4.5 million vertices. And loads 100 megabyte. Oh yeah, no. Oh yeah, it came back, and here it is. Yeah. So that's my brain in big. You can slice through it, and then you can download surfaces on demand. The white matter surface, for example. Then maybe the gray matter surface, which are two different brain structures, brain tissue types in the brain. Yeah, I think each is 30 megabyte. Now if I do the volume rendering, yes. So yeah, I think it looks quite cool to see like through the opaque surface, the brain surfaces, the blue ones, you know, and yeah, so that's 4.5 million vertices, like 1.5 million triangles around that, and we get low frame rates, but that's expected. You can look into the ear to see the brain. That's badass now. So yeah, I think you guys got a good idea of what we use WebGL for at the Children's Hospital, and yeah, we are hoping that more people get interested in that, and especially other researchers, other hospitals want to share their data online, and I think that's the right way to go. So the whole presentation, which I made in jimpress.js, where you can embed the WebGL. It's online under babymri.org/Orlando. And thank you so much for listening.
Do we have any questions from the floor? Mic is on its way.
I think I have two quick questions. One was, you mentioned sometimes you have up to 100 megabytes of data you have to transfer. What are the original size for the voxel grid? Like when they do the scan, like what resolution is that at?
Maybe one by one. So it's 256 by 256 by 160. You know.
Gotcha.
So the 1 by 1 by 1 is the voxel size, you know, and then for a brain it would be 256 by 256 by 160.
Gotcha. The other thing was, you mentioned using marching cubes.
Yep.
I was wondering, have you guys thought about just directly doing ray marching in the fragment shader on the volume?
Yeah, that would be I think the volume rendering is similar, no, to this approach. The volume rendering, where you have the volume and then sort it in 3D.
Yeah, well, you would march a ray through the volume in,
Yes.
in a fragment shader. We could talk more after
Yes.
you talk.
No,
about
that yeah, that makes sense for the label maps. You can load a label map just without the volume like this, and then you could do the volume rendering with like a transfer function to show it in color on the 3D. That's true. But the marching cubes is like a common approach, and also to quantify, you know, to quantify a structure, there need to be a surface model to quantify the volume. You can't quantify without this.
Yeah, gotcha.
Great. Thanks, Monty.